This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
What is the difference between mere life and the good life? Aristotle once said, "The good life is a life informed by the principles that express our highest ideals, life as we would like to live it."
The good life is an education that rattles and decenters.
Relationships, sustenance, and aspirations.
A life of reflection and agency in concert with others in pursuit of collective well-being.
The good life is to equate instead with a healthier public life.
Pursuing knowledge, cultivating friendship, preserving freedom, satisfying needs.
The good life is having a language to express your deepest thoughts, emotions, and beliefs.
The good life is when students' eyes light up at the realization that their engineering work will improve other people's lives.
Stay with us as some of UC San Diego's finest scholars share their pursuit of the good life.
Welcome to UC San Diego. Welcome to the Great Hall of International House. Welcome to this, the final offering of the lecture series, The Good Life. As you know, the purpose of this series is very simple. We want to share with you, with members of the community, with faculty and staff, with parents and alumni. We want to share with you some of the greatest treasures of this university. And those treasures are its professors, its scholars, and its artists. In a few minutes, my colleague Stephen Cassidy will introduce tonight's speaker. I did want to first thank our guests and then talk about past and future. Our series is made possible by generous collaboration and sponsorship by units around campus, as well as from the community at large. The Chancellor's Associates, Parent and Family Giving, UCSD Television, which has been recording each of these shows, the Office of the Vice Chancellor of Student Affairs, some of the divisional deans who have provided support. In each case, we've been able to draw together support from the campus to put together this series. We also have support from members of the community. Kim and Jeffrey Belk are providing sponsorship, the Cubic Corporation, and also the Afsahi Family Foundation. Their support makes it possible for us to provide to you this extraordinary series of talks. So as you know, every beginning has within it its end. All things must pass. This is our last lecture for this series. It's a bittersweet moment, but recall two things. One, every lecture in this series has been recorded by UCSD Television and will be broadcast both on television and is available on the internet, on the UCSD TV and on the YouTube channels. Every show from the previous years in this series, and we think it is an extraordinary way to revisit. If you missed a lecture, then you have a chance to return and see what was said. My lecture, the first, has already been posted, just recently posted. Roger Reynolds' extraordinary spoken performance that was given in the Previs Hall. That too is up. Each lecture with time will come up over the next 2 months on UCSD Television. So you'll have a chance to revisit. Not all is lost. But also, there is the future. We're already planning for next year. We want to return to the community with another set of lectures around a different theme. In this case, we've debated back and forth what the right way of casting this theme is. The central topic is freedom, a concept central to physics, to chemistry, but also to morality and politics, a concept that plays an extraordinary array of roles in our lives. We believe we've settled on a title, Degrees of Freedom, as a way of talking about this series. We considered taking a vote tonight, but we'll just leave it at that. We have a couple of other options: to be free, free reign. I think Degrees of Freedom has generally won out. If you have strong views, please let us know. But our intention will be to bring together some of the most stunning scholars and artists and researchers and teachers on this campus to once again explore a common theme and make it available to all of you. So look for that next year, same time, same channel, same location. So finally, I want to introduce my co-organizer, co-conspirator, the man who is the talent scout for this series, Steve Cassidy. Steve is a professor of comparative literature, associate dean of graduate studies. He will tonight introduce our speaker. Steve.
Thank you, Alan, and welcome everybody for this last in the series. It's a great pleasure to introduce to you tonight a newcomer to UCSD San Diego, Albert P. Pisano. Al Pisano, Dean of the Jacobs School of Engineering since September of 2013. Most important about Al, I was able to detect, after 12 seconds of conversation, that he comes from my neck of the woods. In this case, I should probably say my neck of the woods. Yonkers, Great Neck, pretty much the same thing. Although I must say, he doesn't have quite as bad an accent as some of you Osher people out there. You know who you are. And for this reason, I think he has a direct line to knowledge of the good life and can speak with authority about it, coming from New York. Well, you know those things that you turned off a couple of minutes ago? Please don't turn them back on. Do you have one that can tell the difference between when it's sideways and when it's right side up? If it can do that, the display shifts depending on which way is up. It's owing to a technology that forms part of the specialty of Dean Pisano's work, though I don't think he put that technology in your cell phone. The thing is called an accelerometer. Well, you know how Einstein reminded us about a century ago that gravity is a form of acceleration. And so an accelerometer is a thing that detects gravity in the form of acceleration, the force of acceleration, and it knows which way, therefore, is down. Now, the thing is, how do you take something like that and put it in something this size? And that's where Dean Pisano's specialty comes into play. It's called MEMS, which stands for Micro Electrico-Mechanical Systems. And I can't begin to describe exactly how this functions in your cell phone, but I know that it happens on a very, very small nano scale. And that's the type of work for which Dean Pisano has become quite famous internationally. He is at UCSD the Walter J. Zabel Chair in Engineering. He is a faculty member in the Mechanical and Aerospace Engineering and the Electrical and Computer Engineering departments. He is a member of the National Academy of Engineering. That's an honor bestowed on very few people in his field. He came to us from UC Berkeley, where he was on the faculty for 30 years. He received his education at Columbia University and has had research positions in a number of private firms, Xerox, Singer Sewing Machines, General Motors. As I mentioned, his research interests include a focus on MEMS technology, that's wireless sensors, in some cases for harsh environments, and for a huge variety of applications, in addition to printers, power generation, drug delivery, strain sensors, biosensors, other technologies that do have a tangible impact on the lives of people and thereby contribute to the good life. He's the co-founder of numerous startup companies, and it's really hard to list all of his accomplishments and to imagine how he has done them in his life. In any case, tonight his topic is engineering as a force for the public good. Please join me in welcoming to the podium Dean Al Pisano.
Well, good evening, everybody. And as you can see by that quick motion I made, I just used microtechnology to put this image on the screen. I also thank you for your applause. This is the first time I was ever congratulated for the ability to walk up to a podium. You guys are really generous, and so I think this is going to be a good talk. I could do it in Bronx, Brooklyn, Queens, or Jersey. All right, but we'll try to go for the Queens English on this one. So, that's a double entendre that I did not mean to make. Okay, so let's have a chit-chat. Let's have a talk about engineering as a force for the public good. And as friends of mine say, you know, the situation is definitely serious, but we're not taking it seriously. And let's get straight into it. So first off, I'm very, very pleased to have been selected as the 4th Dean of Engineering at the Jacobs School of Engineering. There is not a long lineage because this, as all entities on this campus, is a very young entity. And despite its young status, it is this engineering school is the 13th in the world for engineering, technology, and computer science. If you follow the academic ranking of world universities, we're the 8th, the whole campus is 8th among the best U.S. public engineering schools. And we are number 1 in the country for biomedical engineering. And many of the things I'll talk about, we'll take a little tour through technology. I love widgets, I hope you do too. Many of the things we'll talk about relate to the biomedical engineering field, which I think is going to become more and more important as we figure out how to operate our societies at full speed while the aging demographics basically move people from the working force to the post-working force. And how all that plays out socially is very important, and there's an engineering role in that as well. We are a student-centered, research-focused school, and indeed, we are also the largest engineering school in California. By any measure, these are ginormous numbers. We have, imagine, 6,500 students swarming this event trying to pick clean what's left of the hors d'oeuvre table. If you turned loose that force, I mean, you know, you'd be rebuilding the carpet and replacing the chairs. A stampede would go through this place. And so I agreed to come down from a job that I held for 30 years and to try to wrangle that huge crowd into some level of organization. And to do that, we put them into 4 academic departments. 6 academic departments. They range from bioengineering and computer science through electrical engineering, mechanical and aerospace, all the way out to the very small nano and the very big structural engineering. And some of you may be amused to know that we're notorious as having the world's largest outdoor shaker table, which is a large concrete platform used to shake buildings. We were also notorious as one of the few schools that built a building on it, set fire to it, and shook it to pieces. That's not exactly on the surface for the public good, but figuring out how to make structures that can survive multiple calamities is. And I just want to make a point that for anyone to prosecute this level of research, it means that your faculty are extremely, extremely busy raising money and very busy handing that money over as student support for our excellent quality and highly competitive student body. And so if you wanted to estimate in dollars as opposed to in people, what is the size of this big thing called the Jacobs School of Engineering? It's about a $240 million machine. It's a pretty big machine. So let's shift gears now and talk a little bit about some global trends. Now, I don't know how many of you are following some of the business literature, but there's a book called Abundance. And the subtitle is The Future is Better Than You Think. And this book is making its way through the offices of all the CEOs, and indeed it's made its way through my office. And one of the premises of the book is that there are technologies that are growing at such high rates that they will help contribute to an elimination of hunger, a lack of medical care, lack of clean water, lack of energy. They will contribute to the end of these shortages in 20 to 30 years. That is a very bold claim on the purpose of an author, and then he has 184 pages to convince you that he's right. The interesting part he points out is that there are emerging in the world exponentially growing companies, exponentially growing industries, exponentially growing technologies, things that are growing much faster than anyone could believe. So for example, the sensor industry is growing at over 24% per year through the recession. Electronics is growing at about 1% per year. So there are these industries that are actually generating jobs, generating money, and being used to increase the economic engines for the entire world. And indeed, if you listen to some of the analyses from the Gates Foundation, they are predicting that if we play our cards right, by the current definition of poor, there will be no poor countries on Earth by the year 2035. If we make the right investments and allow these exponential growing organizations, products, and technologies to keep going, you have a chance of wiping out poverty, according to the standards that we apply today, by the year 2035. And I say that engineering indeed has a big role in that. So let's start looking at specific things that engineering as a force for the public good can achieve. On the upper left, you see a newborn infant that is wearing a special kind of sensor, and I'll relate that a little more details in a slide about it. But I just want to point this out. That sensor is as thin as a sheet of paper, and it's as big as a postage stamp. And you may not think that that's such a big deal, but a critically ill infant receives many sensors attached to their body over the course of the intensive care. And believe it or not, a significant source of injury and occasionally mortality is due to the fact that baby skin is so sensitive. As you apply and take off these sensors, you actually damage the skin and the child develops an infection. So there's a case where just by shifting to an innocuous technology, you can actually immediately start saving lives. You can imagine that generating more energy or transportation safety, or in fact, looking at technological solutions for problems for the developing world, built with materials available in the developing world by people living in the developing world, may be a very powerful way forward to both build the economy and to remove some of the problems there. And so I'll offer this as one example. The island of the Philippines has 1.4% of the world's population. The island of the Philippines, the islands of the Philippines, has 15.7% of the world's death by landslide. That is an enormous social problem for them. You have villages being wiped off the face or wiped off the face of the earth at the foothills where the landslides are occurring on a regular basis, and the recent disasters there due to the typhoon is just a part of that problem. What if you could make a sensor so rugged you could hit it with a hammer? What if that sensor could be bonded to a metal rod that you just hammer into the ground? And what if you arrange to put an array of these on a troublesome hillside? What if you could measure the microscopic subsurface movements that occur 4 to 6 hours before the land actually slides? So it turns out that landslides have precursor events. The essence of a landslide is the water percolates about a meter or so down until it lubricates a level of gravel that separates the hard rock of the hill from the carbon-rich topsoil above the gravel. So what if you could start measuring those small motions that occur first? And that indeed is the topic of a joint research project between our university and the University of the Philippines that I'm setting up, so that you could actually hammer rods into the ground. You ask the local workforce to do nothing more sophisticated than hammer a rod a meter into the ground. And for a large segment of the geology, you can start looking at coordinated movements of the soil. You can imagine, right, the northeast corner of the valley, edge of the valley wall, all the soil there suddenly moves a quarter of a millimeter in the course of an hour. You say, well, wait a minute, that sounds like a warning sign to me. And indeed, we are working with the government of the island of the Philippines to put this project forward as one of the first landslide warning systems. And if that works, you can imagine 1,000 other uses for a technology like that. Let's do another what if. And so we'll start with a what if, but the answer is yeah, it's already in progress. So what if we could make very, very, very thin electrical systems such that even when you squeeze them or stretch them, they keep functioning? Has anyone here ever tried stretching a laptop about 10% bigger? I don't think you're going to get, well, you might do it, but I don't think the laptop's going to work afterwards. All right? So imagine not just a sensor, but the components necessary for wireless communication, antenna, capacitor, transistors, that you could actually tattoo. And I don't mean with the needles, I mean as a transfer tattoo, temporary tattoo. You could actually tattoo onto the surface of your skin. Well, this is a picture of it, and it works. This sensor here makes a measurement of the EKG, the electrical signals that you can sense at the surface of the skin, and gives you a Wi-Fi link so that you can indeed make an assessment of that signal. Now, what might you do with a sensor like that? Well, you know, if you had someone at risk for a health problem, this is probably the most innocuous, unobtrusive, easy-to-use way to help keep track of someone's health that I know about. And you also could imagine that that Wi-Fi link on your cell phone would be talking to the antenna on this patch. And you could imagine an app that would take that signal and call the right people if the signal were out of an acceptable range for that patient. So, as we look at the healthcare problems that the nation faces, we're all going to come to the realization that the better job we do with preventive healthcare, the lower the cost of the healthcare system. Imagine you had an early warning EKG system you could sign up for if you had any worries about your health. That sounds like an incredible benefit for the public good. And indeed, there have been prototypes tested on women in maternity clinics. So imagine, you could either do this, or you could replace all of that with that. Or imagine some poor child is born with some congenital birth defect, and you have to put that child in an intensive care unit. So you could do it this way, which is the way it's done, or you could do it this way, which is the way it could be done. I don't know about you, but if that child could speak, I think we know which way the vote would go. What if we were thinking about actually trying to make an artificial pancreas? And if you look in the literature 30 years old, you find very simple concepts like this. Oh, I got to embed a big piece of plastic and got to refill it, and I've got all these subcomponents. Oh, and by the way, after about 3 weeks, the body recognizes this thing as a foreign entity, and it wraps it with a membrane of cells that isolate it from the body, and it doesn't work anymore. Well, imagine that Professor David Go in our own bioengineering department has developed a way to put a coating on that sensor so that even after a year, the body does not reject it. Imagine that long-term implant could be functioning as an artificial pancreas without you worrying about it. Sounds like a dream for the diabetic population. My dad communicated to me a few days ago, can you sign me up for the first one? We're in animal studies right now, but I think I got one volunteer and close to home that's ready to go. But you know, we don't have to talk about things for the public good that touch exactly on people. Why don't we talk about things that impact the environment or things that impact our cultural history? So let's imagine for a second that I wanted to trace the whereabouts of the whale shark, or I wanted to rehabilitate a certain habitat which has been impacted by human intrusion, or perhaps I had some archaeological dig in a very inaccessible place and I needed to do some sort of pre-mapping of it so I know exactly where to dig, because digging in 30 feet of water is actually a pretty tough thing to do. Imagine you could start thinking about things like that. You could track the motions of wolves, even smaller wildlife. These are all actual projects running with partners. San Diego Zoo Global, for example. And what we're looking at is the development of a whole bunch of animal tracking devices that enable you to figure out what these animal populations really are doing. Now, you know, a lot of times when you have urban sprawl, the first thing the humans accidentally do are wipe out the predators that keep other populations under control, right? That's why you can't throw a stick 10 feet in any direction in Del Mar without hitting a raccoon or a skunk or a possum. All right, they all have, oh, what is the natural predator of a skunk? That one really, like, hi, someone wants to chase down a skunk? The automobile is one, yes, but before Henry Ford so designed it, the owl, right, and it preys upon the young, thank you. So, you know, owls really don't get along with human construction that well, and they're the first people to move out, right? And so therefore the populations run out of control. What if you could track what's really going on and try to figure out how to alleviate basically owl flight from the neighborhood as soon as those humans move in? There is a myth that air quality can be known locally. And that's not true. Air quality in every urban region is a very strong function of position. Anyone ever walk or bike along the 56 or the 52, you know, those biking paths? If you're on the downwind side, you're picking up a lot more automobile exhaust than you are on the upwind side. Urban environments are not easily measured by homogeneous numbers. You know, what is the temperature of San Diego? All right? There's a phone app that'll give me a number. I don't believe it for a second because I'm not exactly where that thermometer was, and I think it's 6 degrees warmer than what they're saying, and then 10 minutes later I think it's 5 degrees colder. So there's a myth that has to be broken that, oh, air quality is something you measure for a region. No, it is not. Air quality is the quality of the air you are breathing. Or better, the quality of the air my children in school are breathing. Or the quality of the air that my father with emphysema, true story, is breathing. That's the air quality I want to know. Air quality is local. If you talk to the EPA, they will first identify a known polluter, calculate the average wind direction, and put a monitoring station downwind of that polluter. If the wind's blowing in a different direction, you're not making any measurement of what that polluter does. So locality is the deal. What if you could retrofit every single cell phone as an air quality sensor? And indeed, there are small companies that are already putting forward 4mm by 4mm chips. Just take the tip of your pinky and look at that straight on. That's about the size. That's the overall size of the device. And that chip measures the top 6 of the 10 measures that the EPA uses to evaluate air quality. Imagine then that every single one of us here had one. And because the cell phones all know that they're in close proximity, we all know that everyone should be coming up with a similar but a little bit different number. And if someone came up with a number outrageously out of scale, we automatically know which one is broken. Now, the power of the crowd harnessed to protect the air that we breathe, I think that's engineering for the public good. Or what if at the place where the fovea is located, the fovea is the location where the optic nerve comes into the eye, and it's the little tiny blind spot that we all have. There's an optical trick where you can make a little dot disappear by putting it in the right position in front of your eye. Well, what if you had one form of macular degeneration, and in the vicinity of the fovea you had either high blood pressure, disabled the cells, or one of a number of other debilitations, you would have vision similar to this. One part of your vision is occluded, and there may be those of us here who have had to endure a detached retina and the process of getting it reattached, right? Watch for the shadows in the corner. That's when you know the edge is detaching. Well, what if I told you that you can grow human eye neurons on silicon nanowires, where a nanowire would be 20 or 30 nanometers. Let's put that into perspective. Let's see, if you're a swarthy New Yorker, your hair is 60 microns in diameter. But if you're from the refined folk uptown, it's 40 microns in diameter. That's actually true, and I won't get into why. 40 nanometers is 1,000 times less than that. We're going to make individual wires that could be almost 1,000 times smaller in diameter than the diameter of your hair. And if they're that small, cells can grow around them, through them, over them. It just doesn't matter. A structure that small, the cell is not equipped to detect. And if you work the chemistry right so that what the cells do feel is a certain substance on the surface of the silicon, this picture shows that compared to the density of the photoreceptors in your eye, we can build an identical density of nanowires and indeed encourage tissue cells to grow on that material. What if we could implant into your eye a very thin, flexible chip that could restore the functioning of your retina if you suffered from macular disease? Other faculty are looking at how would you use signals from the brain to control an artificial arm. People have accidents, people have injuries. The interesting thing here is we are not talking about sticking all kinds of, what we're talking about is a direct reading of the electrical signals in the brain itself. And those of us on the campus who are mapping the human brain can tell us, oh, here's the area that does large muscle motor control, et cetera, vision center, whatever. What if we could actually interface electronics directly to the brain? And indeed, we have on our faculty someone who has actually done that. And to prove it, there is a chimpanzee, I believe, who can control a prosthetic arm with thought now and actually feed himself a banana. So this is getting to be an interesting way to restore what's going on with injuries. I don't know about you, but you know, I have a teenage son, just not quite 20, sophomore in college, University of Illinois. Go son, good going, good school. He drives a car, Some of us may remember worrying about your teenage children driving a car. Over the world, there are 1.2 million people who die as a result of a crash on a road. Isn't that an astounding number annually? That is approximately 3,200 deaths per day. A lot of these accidents occur in what is called the last second. If you would put the brakes on 1 second earlier, you would have avoided the crash. If you turned the steering wheel 1 second earlier, you would have avoided the crash. 1 second. If you study the crash reports, you need 1,000 milliseconds, 1 second, to change the course of history and avert that crash. So literally every second counts. What if you had a warning system? What if you had a warning system that gave you that extra second? What if you had a computer system in your car that was anticipating where everything was going by keeping track of its speed and heading, and gave you that extra second? Most of us would probably not use it very often because we're paying attention. And that one time, when you get distracted, the newspaper blows across the road and sticks to the windshield, or somebody beeps, or there's a activity on the side of the road and you make that half-second glance. Just that one time. That would be engineering as a force for the public good. And indeed, we're looking at all these devices, and in fact, you may have seen a recent Japanese car commercial in which they're saying, hey, we're actually bringing it to market. Solar energy is an interesting energy source. The sun doesn't shine when we tell it. So therefore, we make solar energy at inopportune moments. The world needs, most of the industrialized world has a power peak in the morning that begins at 5 or 6 a.m., peaks at about 9. So on a rainy morning, your solar farm is not contributing to your ability to service the needs of your population. So what that means is you need some other form of energy to balance solar. And that has to be a schedulable energy source. And it's typically a gas-fired turbine, a natural gas burning gas turbine. Well, the problem with the gas turbine is it takes a while to warm them up. It takes a while to bring them up to speed, get a power generation going. It takes a while to turn them off again, and when you turn them off, you're stuck with another restart cycle, and you can't bring them back online again. So imagine a world in which we blend localized weather forecasting, including the tracking of individual clouds. So we will give you, for automobile accidents, 1 second counts. For gas turbines, 11 minutes counts. What if we gave you an 11-minute warning that your solar farm was about to go under an extended shade for 18 minutes? What if you knew that really accurately? As in, the sun load right here is going to change. You would have a chance of shifting your energy generation, and you could keep that farm running in a much more productive, the union of the two power sources would be much better able to carry the energy load. And indeed, our faculty are looking at doing exactly that, and we're actually getting very, very good at predicting the actual energy that hits the ground due to the sun. If you just use the weatherman, he's off by a little factor. You notice at this moment in time, we predict this much. The actual is this much, and that's what the normal weather report would give you. That's a factor of 8. I don't know about you, but if you're off by a factor of 8, light bulbs either explode or stay dark. Hi, I put 1,000 volts in my light bulb. That's 8 times higher than 120 volts. And if you put 10 volts in it, then you don't get any light at all. What if we could simplify the way effective drugs come to mitigate the effects of disease? Now, many of us have drug regimens that we're on. You take various pills for various things, and they talk about all kinds of side effects, right? Well, you know, all of these issues are exacerbated if you do a systemic delivery of drugs to the body, right? I'm going to soak your entire body in a drug because I'm going to have you take a pill, and only one tiny part of your body needs that drug, right? You take enough aspirin to soak all your tissue when all you have is a toothache. You know, that's tough on your kidney and your liver and a bunch of other things. What if we could work a two-fisted approach to delivering a drug and releasing a drug exactly where it's needed? What if we could make these 200 nanometer spheres, so that's a fifth of a micron, and there are 60 of them to your hair, so this is 1/300th the diameter of your hair. What if we could make a sphere which contains a very powerful drug that would have lots of side effects if it were systemically distributed in your body, but no side effects if it was at the exact right spot? What if that sphere were covered with the material that makes it stick to that exact right spot? So even if the spheres are floating in the wrong place, eventually they all agglomerate into the right spot. And then what if you could systemically dose a non-toxic trigger? So for example, here, this is a cancer-fighting approach. We will take the nanosphere, it will attach itself to a tumor. Inside the sphere is a very powerful toxic drug which will kill the local tissue. Well, the local tissue is the tumor. We'd like that to happen for sure. But how do you trigger it? Well, you could take this completely innocent to the rest of the body trigger drug that would diffuse into the sphere, release the toxic drug, and it would diffuse out. And the whole trick with this sphere is that these holes are set to the right. And you notice we're not only making a sphere, but we're drilling little bitty holes in it. And we're making these spheres thousands and thousands at a time. So that's a little interesting engineering job. I haven't threaded a needle recently, but you know, the thought of trying to do it for something, sounds really wild, right? Little tweezers, putting a molecule in each one. So what if you could make that dual porosity sphere, as we call it, and then use a two-signal system? You put the toxin in the sphere, and then you have a systemic trigger that says, okay, let them have it. That sounds like an interesting way to attack disease in a way that disease doesn't anticipate. Well, you know, you could work the opposite of that. What if the sphere had an affinity to absorb deleterious drugs in your deleterious chemicals in your body? And so here's a sphere. We call it the nanosponge. It's actually fabricated in such a way that it's covered completely with red blood cell membrane. And you know what that means? That means the body accepts it as one of its own. Because when the body tests it, it says, oh, red blood cell. Talk about the wolf in sheep's clothing, right? Except that this wolf consumes all the things that you don't want in your body. So you could flip it the other way. And indeed, we're even thinking about using this to deliver vaccines. Imagine a world in which if you injure yourself and my brother once cut a piece of skin off his hand, and that was a big deal to get that grafted back on. Imagine that you could make the thing that you accidentally cut off. You know, a lot of people print tissue to try to make artificial organs, but you know what the toughest part of that is? You got to print things like conduits for nerve endings, and you've got to print little bitty capillaries to carry circulating blood, right? I mean, it doesn't pay to graft just a piece of plastic onto your body. That doesn't integrate itself into the rest of your metabolism. So we're looking at the tough stuff. Let's start talking about how to make the vascular system, how to make the veins and arteries. Let's talk about how to make small conduits which will guide the growth of nerves so that they go back to where they need to go. Because, you know, if a part of you is accidentally cut off, there's a whole bunch of stuff that is removed, but you've got to establish all the reconnections. What if we imagine a world in which you might actually have head-to-body wearable sensors, where these sensors do a whole bunch of things? So for example, and you mentioned accelerometer earlier on, right? Which way is gravity? If you wore an accelerometer right at the center of your chest, just by measuring which way gravity is, I could estimate if you sit up, stand up, lay down. If while you're laying down, I can estimate your breathing rate. If you're standing, I can estimate the rate at which you're walking or running with one sensor set located on the surface of the chest. Imagine a world in which the drug therapies that you get understand what you're doing and deliver the right drug at the right time. Any of us who are on any kind of serious therapy know that there are many drugs that, if you take them at the wrong moment, they are totally ineffective. They don't have any efficacy. What if we knew? What if the drugs were released? What if the therapy was made at the right time for you? A lot of problems occur when people are over-medicated or medicated with the wrong thing, and you go through all these mysteries about how do you get the number of medications reduced. What if we just knew what was the right drug at the right time for you? Maybe a sensor system could do that. My internal clock says I'm getting close to the time limit. I have 5 minutes? Yeah, okay. Remember, I'm a faculty member, right? I'm programmed to talk for 50 minutes and shut up. And the internal alarm clock went, and there's no clock here. You know, I'm looking at all of you, seeing who's got your wristwatch pointed in my direction. But the internal alarm went off, and okay, it's still good. It's still good. All right, I'm glad. My circadian cycle is still good. Most of us drove here today. You drove over a bridge, I'm sure, or a conduit. You drove over a ramp. Hopefully you didn't. Well, was it good to have driven over a skunk? I don't know. The other predator that we mentioned today. If you did, I hope you parked your car downwind of the center. The built infrastructure is something that we all take for granted, and you have no idea how much money it would take to replace even a subset of it. Right? This is something that we've spent 150 years building, and I don't know about you, but I wouldn't want to spend all of that in 1 year to try to replace it. So taking ever better care of it is one of our jobs. And we have faculty, of course, that do everything from experimental testing to dynamic models of how things break. Not because we're interested in breaking them, but we're interested in making sure that they don't break. And more importantly, we're interested in finding the least expensive way to get the biggest strength increase in the built infrastructure so you can retrofit to handle a large event earthquake or maybe a flood or something like that. So there's a whole bunch of efforts where we look using computers and various instruments exactly how materials behave, including how exactly a projectile breaks through a surface. And you can see here at this third time lapse that as the projectile goes through, yeah, a lot of stuff goes along with it, but there's a bunch of stuff that shoots out backward. Now, you know, when you have an earthquake, windows shatter, all sorts of stuff breaks. What if you could design buildings so that all that shrapnel, all those things that deliver the secondary injuries, what if all of that was engineered into a safe scenario? That's what we're looking at doing. This applies to airplanes and a whole bunch of other devices, including looking at vehicles that travel in space. Let me end on this one. Wind energy sounds like a very interesting source for renewable energy. But you know, if you just decide to populate a hillside willy-nilly with turbines, not only does it look like a hillside of turbines, no longer the hillside of flowers, but you know, you reach much faster a point of diminishing returns. It's at UC San Diego that we actually calculate this effect for the first time. When you put a wind turbine anywhere, and the wind goes past it, that turbine disturbs the flow of the air, right? It has to. That's how it's extracting the air, energy from the air. The air doesn't move the same way. There is an optimum way to stack turbines in arrays so that they minimally affect each other and you get the maximum extraction of the energy from the air. Well, what's that for? Well, what if I told you that we could have half as many turbines and generate the same amount of power if we didn't have the interaction among the turbines, and instead of having a hillside with 10 of these things, maybe it's only 5, and maybe that becomes something that people can live with. Maybe instead of 4, it's 2. So, an indirect use. All right, so let's jump to the end. I always put more material than I need. If you wanted to walk among 200 hyper-excited students, each standing in front of a poster, each one eager to tell you what they've been doing and why, then please come to our research exposition on April 17th. We will have representatives of over 140 companies there. You are all invited as well. The students are desperate to tell the rest of the world what they do, and any interest you show would be rewarded with an endless prattle of all the details of the project. And for relief, when you're facing the poster, you may turn 140 degrees to the left and embrace the refreshment table that we'll have there for you so that you could shake off the overactive student who's trying to convince you that you must listen to the bitter end all about his project. Okay, so let me at this point say thank you very much. I tried to take you through a technology tour. I'm very happy to be the Dean of Engineering here at the Jacobs School. It's a great machine, and it is my unwavering determination that it will continue not only to be a force for the public good, but an ever-increasing positive force for the public good. And I thank you all very, very much.